Hello guys, hope you all are doing well. So in this video we will see the remaining 4 question of 2010, that is 2010. Then we will solve 2011 and then 2012 and onwards, because I am seeing that most of the people are interested in only last 15-year paper. Okay, then after solving those questions, if time we will have, if uh, time will be there, then we will solve the remaining 2002 2010. Okay. So without wasting time, we'll see first question. So this is the question. You can see we have to calculate the overall heat transfer resistance, not coefficient, okay, resistance. So very first, this is the counter current, co-current conditions. Okay, this is the heat balance equation. In the question, it is clearly written heat capacities of both the fluid streams are same. So you will have this, then this T is equal to 70. Now for counter current, theta m will be changed, theta m will be 80 degree Celsius in this, because 150 minus 70 will be 80, 110 minus 30 will be 80. That means we will use arithmetic temperature difference. So AMTD will be 80 in counter current case. In co-current case we have LMTD 70. So this is the answer. Okay. Next question. Plant produces phenol. The variable cost in rupees per ton of the phenol is related to the plant capacity. This question is important and I will explain you. This question is a little bit important. Wait. Okay. So, very first, a plant produces phenol. The variable cost in rupees per ton of the phenol is related to the plant capacity P tons per hour. Okay. Variable cost is in rupees per ton. Fixed charges rupees per day. Selling price phenol is 15 per ton. Very first, note that. Sorry. Here. Very first, note that P is in ton per day. Variable cost is in rupees per ton. Fixed cost is in rupees per day. Okay, and selling price is in rupees per ton. Okay, so we have different units. Now for optimal plant capacity, question 50, for minimum cost per ton of phenol, we have to minimize what? Minimize rupees per ton. That is cost per ton. Okay, so I think you have noted down the units, because I am going to erase this. Just remember the units. In this question, you have to deal with the unit. Okay. Now, so we require to minimize the cost per ton. Okay. Now, variable cost in is rupees per ton. Fixed cost was in. So we have to minimize the rupees per ton. So variable cost is already in rupees per ton. So don't touch it. Okay, don't touch it. But see, fixed cost is in rupees per day. If I divide by P, then rupees per day into ton per day, and day will cancel out. So rupees per ton. And what is the total cost consists of? Fixed cost plus variable cost, that is total cost. Integrated, differentiated for minimization, maximization. Okay, we will get E is equal to 141 degrees Celsius. Okay, now for break in capacity, this is the equation. Note down the equation. This is the equation. Okay. In most of the cases, we neglect the profit if it is not written in the question. Okay. So we'll total sale. See, sales is equal to 50,000. That is rupees per ton. If I am selling P tons, then ton cancel out. This is the total sale. This is the total sale. Selling price for unit into number of the units. So SP is the SP is the total sale. P is the quantity. I can write S into X, where X is the quantity as a general term. General. P, why I'm writing P? Because in the question P is given. Okay. So now C, fixed cost is in rupees per day. So we have to convert it into rupees per ton. Sorry. Variable cost is in rupees per ton. So we have to convert it into rupees per day. Okay, so multiply with P. So you will get your answer after solving this equation. Okay, you get a quadratic equation for break-even capacity. Okay, this is a little simpler question. I think there is no need to explain. So simple component balance, basic mass transfer, putting all the values. Okay, you'll get this. Now 50% efficiency is 50%. That means 50% of this Y we are getting will be in the X. So X is equal to 0.5 of Y. So you will get Y is equal to 1 by 12, your answer. Okay. New Y. Okay. This question. So very first, liquid phase reaction EA is equal to 0. Residence time 2 seconds. CA naught 2 mole per liter. CA 1 mole per liter. Conversion 50%. Apply performance equation. So this is the performance equation. Taking tau n this term. Putting the value of I minus Rn, which is shown in the box in the middle. K is equal to 9. Now, in the second question, see this and two reactors. Okay. So CA2 is 1, CA1, CA naught. We have to find out. Okay. Okay. So performance equation of CSTR. So this is the performance equation. We will take this one, this tau and this tau. This is the performance equation. If you just convert it in CA form X. So for second reactor, see second reactor tau 2 is 0.2, CA1 minus CA2, CA1 minus CA2, CA2 is 1, 0.5 is equal to where 0.5 came from. So this is come from. Okay. So this is for second reactor. This CA will become CA2. Okay, CA2. Okay, now CA1 will be 1.1. For the first reactor, this CA will become CA1. Okay, so we'll get 1.6. So straightforward. This question is a little bit tricky. Okay, so bye guys, take care. And if possible, then please share and subscribe. It will be a kind of motivation for me. Okay, so bye guys.